Ever think about how addition, something we all learned back in like elementary school, can turn into this crazy complex thing when you start applying it to sets?
It's true. Like, at first you think, okay, addition, I got this. But then some sets come along, and you're like, wait, what? It's a whole different ballgame.
And that's exactly what we're going to be looking at today in this deep dive. It's definitely one for all you math enthusiasts out there. We're going deep into a paper by Melvin B. Nathanson, inverse problems for sumset sizes of finite sets of integers. So get ready, because it's going to get pretty mathy.
This paper, it really digs into how much we can actually figure out about a set just by looking at, well, how big its sumsets are. It's like, can we do this reverse engineering thing? Can we take those sumset sizes and work backwards, like solving a puzzle to figure out what the original set was?
I'm already hooked. But before we get lost in all the like nitty-gritty details, can you give us a quick, I guess, refresher on the notation we're going to be using, just to make sure everyone's on the same page?
Absolutely. So we're going to be using HA to represent the H-fold sumset of a set A. Basically, that means all the possible sums you can get when you add H elements from set A, and you're allowed to repeat elements.
Okay, so like if our set A is, let's say, 1, 2, 3, then 2A would be 2, 3, 4, 5, 6, right? Because we're adding every possible pair from A.
Right on. You're adding every possible pair, and remember, that includes adding a number to itself. And what we're really interested in is the size of those sumsets. So how many different unique sums do we end up with as we change that H value?
So our sequence of sumset sizes, it might look something like, I don't know, 3, 5, 8, 10. And the challenge is to see what that tells us about where we started the original set.
Precisely. And in this paper, Nathanson, he tackles some really, really interesting questions about these sequences. For example, he talks about this concept of affine equivalence.
Affine equivalence. Now, that sounds a little intimidating, to be honest. What exactly does that mean in this like sumset world?
It's honestly simpler than it might sound. Two sets, they're considered affinely equivalent if you can like transform one into the other. You just got to do some scaling, maybe some shifting. Think of it like the sets 0, 2, and 1, 4. They're affinely equivalent.
Okay, I see. Because you could multiply that first set, 0, 2, by 2/3, and then subtract 2/3, and boom, you've got 1, 4.
Exactly. It's like they're essentially the same set, just stretched out a bit or maybe moved along the number line. And the key point here is that affinely equivalent sets, well, they have the same sumset size sequence. It's like no matter how you stretch or shift them, the number of sums you can make, that stays the same.
That makes sense, just thinking about it intuitively. So are we ready to tackle the big question here, the inverse problem? Can we actually work backwards just from those sumset sizes and figure out what that original set was?
Okay, so theorem 2 in this paper, it gives us some good news, at least to start. It says that if you've got large enough values of H, the sumset size sequence, it becomes really predictable.
Oh, so it gets like boring after a while. No more mystery.
Kind of, yeah. For really large H, those sumset sizes, they basically form what's called an arithmetic progression. It's almost like the set has spilled all its secrets and there's no more surprises left to uncover.
Okay, but hold on. What about the beginning of the sequence when things are still, kind of unpredictable and wild? That's got to be where the real challenge is, right?
You hit the nail on the head. Nathanson, he really emphasizes that it's the early part of the sequence where you find the most information about how the set is structured. It's like those first few sumset sizes, they hold the key to cracking the code of the whole puzzle.
All right, so let's get to the heart of it, that inverse problem.
Yeah.
Can we really figure out the original set just by knowing its sumset sizes? Like, is that even possible?
Well, now theorem 4, that gives us a bit of a reality check. Turns out it's not always possible. There can be multiple sets, and I mean very different sets, that end up having the same sumset sizes, at least for a certain range of H values.
Wait, really? That's kind of mind-blowing. How can two different sets have the same sumset sizes? Can you give us like an example, something concrete for our listeners to really grasp this idea?
Sure. Let's take a look at the example Nathanson uses in his proof for theorem 4. He uses the sets A equals 0, 2, 7, and B equals 0, 3, 7. He sets K to 3, and K here represents the number of elements in our original set.
Okay, so both sets have 3 elements, but they're definitely different. So how do their sumset sizes compare?
So for set A, the twofold sumset, or 2A, would be 0, 2, 4, 7, 9, 14. We get this by just adding every possible pair of numbers from A. Then the threefold sumset, 3a would be 0, 2, 4, 6, 7, 9, 11, 14, 16, 21. Basically, we're systematically adding every combo of 2 elements, then every combo of 3 elements, and so on.
Gotcha. So what about set B? How do its sumsets look?
Okay, so for set B, the twofold sumset 2b comes out to 0, 3, 6, 7, 10, 14, and the threefold sumset 3b is 0, 3, 6, 7, 9, 10, 13, 14, 17, 21. Now, look closely, both 2a and 2b, they both have 6 elements, and both 3a and 3b have 10 elements.
Whoa, that's wild. Even though the sets themselves are totally different, they're twofold and threefold sumsets, they have the same sizes. It's like trippy.
It really is. And this paper shows us that this isn't just some fluke. There's a method to this madness. There's actually a general way to build examples like this for any set size.
So the early part of that sumset size sequence, it can be super misleading. You might think you're on the right track to reconstructing the set, but then, bam, roadblock. Multiple sets could have those same initial sizes.
Exactly. It really highlights how complex things can get, even when we're dealing with an operation as simple as addition. It's like there are these hidden layers of complexity waiting to be uncovered.
This is already getting super fascinating. What other, insights does Nathanson give us into this world of sumsets? What's next?
Well, he dives into the specific type of set, what he calls an interval plus one extra element. Picture this. You have a set of consecutive integers, nice and neat, like 1, 2, 3, 4, and then bam, you throw in one extra element that's like way out there, say 8.
Okay, I can see it. It's like you've got this perfect little line of numbers and then boom, a rogue element.
Yep. And theorem 5 in the paper, it actually gives us this elegant little formula for figuring out the sumset sizes for sets that are built like this.
So problem solved then, right?
Yeah.
No more mysteries with these interval plus one sets.
Not so fast. If you take a look at the table in Appendix A, which it lists out some of these sumset sizes, you'll notice this really curious pattern starts to emerge.
Now you've really got me intrigued. What's so curious about this pattern? What's going on?
It all comes down to how these interval plus one sets, even if they have the same number of elements, can actually overtake each other in terms of their sumset sizes as you increase that H value.
Okay, I'm picturing these two sets racing each other, their sumset sizes growing side by side. How does this overtaking thing even happen?
Imagine you've got 2 of these interval plus one sets. The paper shows that for any point you choose in the sequence, let's call it H1, you can actually create those sets so that their sumset sizes are totally identical up to H1.
So they're like neck and neck at the start of this race.
Exactly. But then get this. After H1, one set starts cranking out more sums than the other consistently.
Whoa. So one set suddenly surges ahead and the other can't catch up no matter what. That's pretty surprising. What does that tell us about the fundamental structure of these sets?
It's this fascinating peek into how even the tiniest change in a set's makeup, that one extra element, can have this dramatic impact on how fast its sumset sizes grow. It's like, whoa, the power of 1.
This is absolutely mind-blowing. We started with simple addition, and now we're in this world of sumsets with hidden patterns, sets racing each other, and discoveries around every corner.
And we're just getting started. There's a whole lot more to uncover in Nathanson's paper, including some open problems that are guaranteed to keep mathematicians busy for, well, probably a long time.
Well, don't leave us hanging. Tell us, what are some of these unsolved mysteries that this deep dive has uncovered? Give us the good stuff.
One of the big ones, it's actually problem 2 in the paper, and it asks this question that seems pretty straightforward at first. It says, if you have 2 sets, right, with the same number of elements, and at some point one of those sets has a larger sumset size than the other, does that mean it's always going to have a larger sumset size? From that point on, is it always in the lead?
I feel like just intuitively you'd think, yeah, probably. Once a set's in the lead in this sumset race, it seems like it should stay there. But, I mean, we've already seen that intuition can be kind of dangerous when you're dealing with sumsets, right?
Right, and that's what makes this problem so interesting. It's like, okay, our gut feeling might say one thing, but can we actually prove it? Or maybe even disprove it? That's where the real fun begins.
So does the paper give us any clues about which way it might go? Does Nathanson, hint at an answer?
Not really. He leaves it as this open question, something for, future research to tackle. It's like he's inviting us all to join in on the puzzle-solving fun.
I love that. It's like we're all part of this big mathematical adventure trying to crack the code of these sumsets. What other open problems does he throw at us?
Problem 3, it kind of goes in the opposite direction. It proposes that if a set starts out with a smaller sumset size at some point, then it's always going to have a smaller sumset size. For all the larger sumset values, it's stuck behind.
So if you fall behind in this sumset race, you're basically doomed. You can never catch up. That's kind of harsh. What's the thinking behind that? Why would being smaller early on mean you're, like, permanently disadvantaged?
It's a really interesting idea. It's almost like those early sumset sizes. They give you a peek into the underlying structure of the set. If a set isn't producing a lot of unique sums early on, it could mean there's something about how it's built, like a structural limitation, that prevents it from ever generating as many sums as another set that might be structured differently.
Okay, I can see that. Like, the arrangement of the elements within the set, it could have these subtle effects on the sum set sizes. It's like some sets are just inherently better at making unique sums than others, you know?
That's a great way to think about it. And then there's problem 4. And this one really goes to the heart of the inverse problem. It asks, what can we actually learn about how a set is structured just by looking at that sequence of some set sizes? Like, is that even enough information?
That's the million-dollar question, right? We've been playing detective this whole time, trying to use those sum set sizes to figure out what the original set looks like. But is that even possible in a general sense? Can we really decode the set's blueprint just from its sum set fingerprint?
It's the ultimate challenge. And unfortunately,
Yeah.
the paper doesn't give us a clear-cut answer, but it does lay the foundation for, future research to tackle this really deep question.
It feels like this deep dive isn't just about finding answers. It's about finding new questions, pushing the boundaries of what we know about sets and addition.
Exactly. And that's what makes mathematical research so exciting, right? Every answer you find often leads to more questions, and each discovery opens up a whole new world to explore.
Speaking of exploring, what about problem 5? Where
Yeah.
does that lead us?
Problem 5, it takes us into the world of what are called restricted sumsets. It's like we're adding a new rule to our game. We can still add elements from the set, but now we're not allowed to repeat any element in a given sum.
Ooh, that's going to make things even more interesting. I can already imagine how that would shake things up with the sum set sizes, make that inverse problem even trickier.
Absolutely. It's like we're narrowing down the possibilities, focusing on a specific subset of all those potential sums. And that restriction, it might actually reveal even more about the structure of that original set.
It's wild how even a small change to the rules of the game, like not repeating elements, can have such a big impact on how these sum sets behave. What about problem 6? Does that take us in a completely different direction?
Problem 6, it goes beyond our usual integers and takes us to this interesting world of lattice points.
Lattice points. I'm a little fuzzy on that. Can you remind us what those are again?
Think of a grid, like graph paper. Lattice points are those points where the grid lines intersect. They're basically coordinates in multidimensional space. And problem 6, it asks if we can take all these cool ideas we've been talking about, sum set sizes and inverse problems, and apply them to sets of lattice points instead of just sets of plain old integers.
Whoa, so instead of adding numbers on a number line, we're adding, like, vectors in multidimensional space. That's some next level stuff. My brain's doing backflips trying to picture that.
It's a pretty big jump, but it shows how powerful these mathematical ideas can be. The stuff we've been exploring with sum sets, it might have applications in other areas of math too. It opens up a whole new frontier for research.
This deep dive has been a whirlwind. We started with the basics, like what even is a sum set? And now we're talking about lattice points and these mind-blowing open problems. It really shows how deep and beautiful math can be, even when you're just dealing with something as seemingly simple as addition. Okay, I think we're ready to tackle theorem 5, the one that dives into those interval plus one element sets. I'm really curious to see what Nathanson found out about their sum set sizes. It sounds pretty intriguing.
Yeah, Theorem 5, it's a pretty cool one. It gives us this really nice, neat formula for figuring out those sum set sizes for these specific types of sets. Remember, we're talking about sets that have a bunch of consecutive integers, like in a row, and then one extra element that's kind of off on its own outside of that sequence.
Right. Like that example we talked about earlier, 1, 2, 3, 4, 8. The first 4 numbers, they're all cozy together, and then hey, it's like, nope, I'm over here.
Exactly. And the formula that Nathanson came up with, it really captures how those two parts of the set, that consecutive interval and that extra element, how they work together to determine the sum set sizes. It basically says that those sizes depend on two main things: how long that interval is and how far away that extra element is from the interval.
Okay, yeah, that makes sense intuitively. I can see how those two things would play a role in how the sum set grows as you add more elements. But can you give us the actual formula, for our listeners who are really into the math and want to see the specifics?
Of course. So let's say our set is A, and it looks like this. A plus 1, A plus 2, A plus K1B. Here, A is the first number in our interval, K is how many numbers are in that interval, and B is our lone wolf element, the one outside the interval. Now, the formula for the size of the H-fold sumset, which we write as HA, is this. HA, H plus 1K if H is less than or equal to BAKK, and HA, HK plus BA if H is greater than BAKK.
Whoa, okay, that's a lot to take in. But it's pretty amazing how he managed to, like, condense all that information into one formula. It's pretty elegant when you think about it.
It really is. And the fact that he was able to actually prove this formula using mathematical induction and a really clever analysis of how those sums are created from the set's elements, it's super impressive.
I'm guessing the proof is pretty involved. Would you mind, like, walking us through some of the main ideas? I think it would be really cool for our listeners to see how he put it all together.
Sure. So the proof, it basically has a few key parts. First, he sets up what's called a base case, where he shows that the formula works for small values of h. Then he assumes that the formula is true for some random h value, and he uses that assumption to prove that it must also be true for h plus 1. This is a classic way to do a proof by induction.
Right. It's like you're climbing a ladder, and you prove it's true for each rung by using the fact that it's true for the rung below it. But what's the tricky part here? What makes that inductive step challenging in this particular proof?
The hard part is really understanding how adding just one more element to the sum, going from HA to H plus 1A, how that changes the size of the sum set. Nathanson had to look at two different scenarios which match those two parts of his formula.
Okay, let's break those down. What's the idea behind that first case, where h is less than or equal to BAKK?
In that scenario, it's like that extra element B hasn't really gotten a chance to make its mark yet. The sum set is mostly being controlled by that interval part of the set. Imagine it like this. Every time you increase h, you're basically making the range of possible sums bigger by k, which, remember, is the length of that interval.
Ah, I get it. So the interval is kind of the driving force behind how the sum set grows in those early stages.
Exactly, and that's why the formula for that case is h plus 1k. It's basically representing that steady growth that's determined by the interval. But then, in the second case, when h gets bigger than BAK, that's when that extra element B starts to become a major player.
So it's like B finally gets to join the party and starts influencing how things turn out.
Exactly. The sum set isn't just growing by k every time you bump up h anymore. That extra element B, it brings in all these new sums that weren't possible before, and the formula has to account for that.
And that's where the HK plus BA part of the formula comes in.
Yep, you got it. The HK part is from the interval, and that BA is for all the extra sums that B is responsible for.
It's incredible how we managed to, like, capture this whole back and forth between the interval and the extra element in just one formula. And the fact that he proved it with induction, that's really impressive.
It's a really beautiful result, for sure. It shows how math can uncover these hidden patterns and connections, even in something that seems as simple as a set of numbers.
This deep dive has been full of surprises already, but I know there's more to come. What else does Nathanson explore in this paper?
Well, after he proves Theorem 5, he goes on to show a bunch of examples and observations that really shed light on how these interval plus 1 sets work. And all of that leads to this really cool result, which he states as Theorem 6.
Okay, now you really got me hooked. What's so special about Theorem 6? What did he find out?
Theorem 6, it basically says that for any numbers you pick, let's call them k and h1, you can create two different interval plus 1 sets, call them A and B, both with k elements, and make their sum set sizes match perfectly up to h1.
So it's like those racing sets we were talking about, but now they're running side by side for even longer before one pulls ahead.
Exactly. They're neck and neck until you hit h1, and then one set starts making more sums than the other every time. It's a really cool finding because it shows that we can actually, like, build these sets that are designed to behave this way.
That's amazing. We're not just observing these patterns anymore. We're actually figuring out how to control them, like how to engineer these sets to have specific sumset behaviors.
Right. It's like we're becoming sumset architects.
Yeah.
And the way Nathanson proves Theorem 6, it builds on all those insights from Theorem 5, using that formula we talked about to create sets A and B very carefully.
I bet that construction is pretty complicated. Can you give us a quick overview of how it works?
The main idea is to start with two intervals that have different lengths, and then you have to choose those extra elements very strategically to make sure the sum set sizes stay the same up to that h1 point. Nathanson lays out a specific method for doing this, and it relies on that formula from Theorem 5 to pick the right extra elements.
Okay, so it's this delicate balancing act, making sure those extra elements keep the sumset sizes in sync for a while.
Exactly. And what's cool about the proof is that it shows that you can always do this no matter what numbers you pick for k and h1. It's always possible to find that perfect balance.
This is mind-blowing stuff. We've gone from the very basics of sumsets all the way to these super intricate theorems that reveal these hidden patterns and unexpected ways these sets behave. And all from something as simple as addition.
I know, right? And we're not even done yet. Remember those open problems we talked about? Nathanson ends the paper with a bunch of them, and they're bound to keep mathematicians thinking for a long time.
Well, don't keep us waiting. Tell us more about these unsolved mysteries. What are some of the big questions that this paper brings up?
Okay, so one that really stands out is problem 2. It asks if having a bigger sumset size at one point means that the set will always have a bigger sumset size after that. Like, does taking the lead guarantee you stay in the lead?
It seems like it should, right. But then again, we've learned that things aren't always so straightforward in the world of sumsets. It's like those racing sets. What if one has a burst of speed early on, but then gets overtaken later? Is that possible?
Exactly. That's the question, and it's not easy to answer. You'd need to really understand how the structure of the set affects those sumset sizes over the long haul.
It's like a fundamental question about how these sumset sequences work. What other open problems caught your attention?
There's problem 3, which is kind of the opposite of problem 2. It says that if a set starts out with a smaller sumset size at some point, then it's doomed to always have a smaller sumset size after that. Like if you fall behind, you can never catch up.
Wow, that's a bold statement. I'd love to see if that's actually true. Is there a way to prove it? Or maybe find an example where it doesn't hold up?
It's definitely a question that makes you think. You'd need to really dive deep into how those differences in set structure play out as those sumset sizes grow.
This whole deep dive has been incredible. We've uncovered so many cool things about sumsets, from those hidden patterns to these crazy behaviors and all these unsolved mysteries that are just waiting to be explored.
I agree. Nathanson's work is a perfect example of how powerful curiosity, creativity, and clear thinking can be in math. He didn't just answer some big questions about sumsets, he also asked new ones that are going to inspire mathematicians for years to come.
It's been a real pleasure exploring this paper with you, and I hope our listeners are feeling inspired to do some mathematical exploring of their own. Who knows what amazing discoveries are out there just waiting to be found. Thanks for joining us on this deep dive, and until next time, happy learning. Welcome to another deep dive with us. This time, we're going to be tackling sumset sizes
Oh, cool.
in additive number theory. And specifically, we're going to be looking at a paper. It's called Inverse Problems for Sumset Sizes of Finite Sets of Integers
Okay.
by Melvin B. Nathanson. So I'm really excited to dive into this and see kind of what unexpected patterns we might find.
Yeah, it's interesting because it's one of those things where it sounds so simple,
Right.
just adding numbers together, but it can get really, really complex
Yeah.
when you start looking at the different combinations and kind of the sets and sizes and all that.
Yeah, it's like I don't know, it's like a mathematical puzzle in a way,
Mm-hmm.
where you start with these like really basic building blocks of numbers,
Right.
but the way they combine and grow can be pretty intricate.
Yeah, absolutely.
So I guess maybe before we get too far into it, it's worth just like briefly reminding ourselves, what is a sumset? What are we talking about here?
Yeah, so a sumset is denoted as HA for a positive integer H and a set A. And basically, it's the set of all possible sums you get when you add together H elements from your set A.
Okay, so like, for example, if our set A is just 1 and 2,
Right.
the twofold sumset, or 2A, would be 2, 3, and 4,
Exactly.
because those are all the possible sums you can get by adding any two numbers from that original set.
Yeah.
Okay, so that's fairly simple to grasp, I think. But things get more interesting, I imagine, when we start looking at the size of these sumsets and how that changes as we increase H.
Yeah, exactly. And that's where Nathanson comes in this paper. He looks at both the direct and inverse problems of sumset sizes.
Okay.
So the direct problem is kind of what you might expect at first.
Yeah.
Given a set of integers, how do we determine the size of its sumset?
Okay, so like figuring out the size based on the original set. Sounds straightforward enough.
Right.
I'm guessing it's not always that easy.
It can get very complicated, and one of the things that Nathanson did in this paper is, theorem one is looking at what happens when you get larger and larger sumsets. So you're basically repeatedly adding a set to itself. And what's fascinating is he proves that for large enough repetitions, the size of these sumsets can be determined by a formula, and it forms an arithmetic progression.
Okay, hold on. An arithmetic progression. So just to refresh our memories, that means the size of the sumset is increasing by like a constant difference each time.
Exactly.
Right. Okay.
Yeah, so it creates like this predictable pattern, even though the sums themselves can be quite intricate.
Wow. Okay, so theorem one gives us a way to like predict the size of those larger sumsets.
Yep.
What about for smaller repetitions? Does he address that as well?
Yeah, he does. So theorems 2 and 3 in this paper kind of go into those cases and, provide us more tools to understand how these sizes work, even when we're not dealing with these massive repeating sums.
Good. Okay, so we've got some tools for like understanding the direct problem, but you mentioned this inverse problem, and that sounds like where things could get really mind-bending.
Yeah, that's really interesting. So the inverse problem kind of flips the script. So instead of starting with a set and calculating its sumset size, we start with the sizes of various sumsets.
Okay.
And we try to figure out what the original set was.
Oh, wow. So that like we've got the clues, and we're trying to like figure out the mystery set that led to these clues.
Exactly. It's like a mathematical detective case.
Okay, I love that. But I'm guessing it's probably not always straightforward, is it?
It's not, and that's what's really cool about it.
Okay.
So one of the things that he talks about is theorem 4. And this is a really interesting finding.
Okay.
It means that you can have different sets of integers that produce the same sequence of sumset sizes.
Wait, hold on. So you're saying even if we know like all the sumset sizes, we might not be able to pinpoint the exact original set?
Exactly, and it's really counterintuitive.
Wow, that really changes things.
Yeah, it throws a wrench in the works.
Okay, so theorem 4 is kind of like throwing a wrench into our detective work here.
Right.
What other kind of interesting things does he discover in this realm of inverse problems?
So he also looks at a specific type of set in theorem 5.
Okay.
And those are sets that are like a consecutive range of numbers with one extra number outside of that range.
Yeah.
So like 1, 2, 3, 4, 7.
Okay.
And he has formulas for how to calculate the sizes of their sumsets.
Okay, so it seems like he's kind of trying to like build up this toolbox of ways to approach these inverse problems and like looking at particular types of sets
Exactly.
to kind of gain a deeper understanding.
And then he also shows in theorem 6 that you can have two sets whose sumset sizes match perfectly up to a point.
Okay.
But then some sets are consistently larger after that.
Oh, so it's like two pieces of a puzzle that seem to fit together for a while, and then all of a sudden one reveals that it's part of like a bigger picture.
Exactly, yeah.
Okay, that's fascinating. It makes me wonder about like the underlying like mechanisms that drive these patterns. Like why do some sets exhibit this kind of dominance while others fluctuate?
Yeah, and that leads us into the open problems he poses in the paper.
Oh, perfect. Because I was going to say those unanswered questions are always the things that get me the most curious.
Mm-hmm.
So what are some of these open problems, and are there any that kind of stood out to you?
Yeah, well, there's 6, and they all touch upon different aspects
Okay.
of this whole sumset behavior. But the one that I thought was really interesting, especially given what we've just been talking about with, this dominance, is problem 2. And this is where he asks whether a larger sumset size at one point always translates into larger sumset sizes from that point onward.
Oh, so it's like, is there a clear winner in this sumset size race, or can
Yeah.
things get a little bit more unpredictable than that?
Exactly.
Okay.
And to kind of really understand this problem, he uses sets A, B, and C as examples to show how these sumset sizes can evolve in different ways.
Okay, cool. I think I'm ready to grapple with the complexity of problem 2, so let's dive into that.
Okay. All right, so let's delve into problem 2 and really explore those nuances with the example you mentioned.
Yeah, I'm excited to see how these sets A, B, and C, their sumset sizes evolve. What does that really tell us about this idea of dominance? Does one set really pull ahead and just stay there? Or do things get a little bit more complicated?
Right, and so he defines these sets A, B, and C, right? And so set A is just the interval of integers from 0 to 4.
All right.
So 0, 1, 2, 3, 4.
Right.
Set B is 0, 1, 3, 6.
Okay.
And set C is 0, 13, 7.
Okay, so we've got 3 sets each with kind of a different structure.
Right.
Set A is just that consecutive sequence, and B and C have got these gaps in them. So I'm kind of already thinking about how that might play out in their sumset sizes.
Right, and so if we calculate their twofold sumsets, right, so 2A, the set of all possible sums of 2 elements from A.
Okay.
It turns out that's just the interval from 0 to 8.
Okay, so that would be 0, 1, 2, 3, 4, 5, 6, 7, 8.
Right.
Which would give us 9 elements.
Exactly. And then 2B gets a little more interesting. It's the union of the interval from 0 to 4 with the set 6, 7, 9, 12.
Okay.
So 0, 1, 2, 3, 4, 6, 7, 9, 12. That also has 9 elements.
Okay, so same as 2A.
Right.
All right.
And then 2C kind of follows a similar pattern where it's the interval from 0 to 4 and then also 6, 7, 8, 10, 14. Again, we have 9 elements.
Okay, so at this point, it's like a three-way tie. They've all got the same twofold sumset size.
Right.
So the structural differences haven't really manifested yet in terms of the size.
Right, but then let's look at the threefold sumsets. So 3A, the set of all sums of 3 elements from A, that turns out to be the interval from 0 to 12.
Okay.
So we get 13 elements.
Okay, so 3A is growing steadily. What about 3B?
So 3B is the union of the interval from 0 to 10 with the set 12, 13, 15, 18. And so notice that there's a gap there between 10 and 12.
Okay.
And so this gap results in 3B having 15 elements.
Oh, so it's pulled ahead of A.
Right. And then 3C, that's going to be the interval from 0 to 11, and then 13, 14, 15, 17, 21.
Okay.
So that's going to have 17 elements.
Okay, so it's in the lead now.
Right.
It's interesting how those gaps in B and C seem to be like contributing to that sumset size or allowing it to grow more quickly.
Yeah, you're right. And so if you continue on to fourfold sumsets, so 4A is going to have 17 elements, 4B has 21, and 4C has 24.
Okay, so in this example, it seems like the sets with those kind of strategically placed gaps, B and C, are outpacing A in terms of the sumset size growth.
Exactly. And so all 3 of them started with the same twofold sumset size.
Right.
But then as we calculate higher order sumsets, they diverge.
Yeah.
And so, this example might suggest that there is some kind of inherent property about the structure of a set that, might dictate this dominance in terms of sumset size.
Yeah, it's making me think about how, like, the arrangement of numbers within a set, those gaps, those clusters, might somehow encode information about its potential for sumset growth.
Right.
It's like a hidden code almost waiting to be deciphered.
Exactly. And so, this is what makes problem 2 so interesting.
Right.
We see this dominance happening here, but does this hold true for any arbitrary set of integers?
Yeah, we need more than just one example.
Yeah.
Is there anything else in the paper that kind of hints at like a more general answer to this?
Unfortunately, no.
Oh, okay.
He just provides this example
Right.
as a way of saying, hey, look, this is a complicated problem.
Gotcha.
But he doesn't really give a definitive answer as to, whether or not that's always going to be the case.
Okay, so problem 2 remains unsolved. What about some of these other open problems? Are there any that kind of shed more light on this or offer different perspectives on this sumset growth?
Yeah.
Yeah, so what about problem 1? Does that tie back into this idea of dominance at all?
Yeah, so problem 1 is kind of an interesting twist on that idea of dominance. So it asks if we can have sets whose sumset sizes kind of fluctuate.
Okay.
So, one set might have larger sumsets at certain points, and then the other set might take the lead later on.
Oh, so instead of having one just being dominant, we have this kind of like back and forth, like a mathematical tug of war.
Exactly. Yeah, it's a really cool idea. And he actually uses those sets, A, B, and C, to illustrate this.
Okay.
So remember, A is the interval from 0 to 4, B is 0, 1, 3, 6, C is 0, 13, 7.
Right, and we saw that they all had the same twofold sumset size, but then the threefold and fourfold started to diverge and C kind of pulled ahead.
Exactly. But now if we just focus on A and C.
Okay.
Initially, A is larger because it contains more consecutive elements.
Okay.
So the size of A, denoted as like the absolute value of A, that's 5,
Okay.
which is bigger than the size of C, which is 3.
Right, so A has a head start, at least in terms of like how many elements are in the original set.
Right. Yeah, but then when we look at their twofold sumsets, remember, both 2A and 2C have 9 elements.
Right. Okay. Yeah. So it's like A's initial advantage has vanished.
Right. And then when we go to their threefold sumsets, 3A has 13 elements, while 3C has 17.
Oh, okay. So now C is in the lead.
Right. So we have this like flip-flop
Yeah.
where A starts bigger than their equal, and then C takes over.
Wow.
And then if we go to the fourfold sumsets, 4A has 17 elements, 4C has 24.
Okay. So it's maintaining its lead.
Yeah, so this example shows that fluctuation is definitely possible.
Right.
But then problem 1 is asking, well, can we get even more flips?
Yeah, like could A regain the lead later on down the line?
Exactly, yeah, like what happens at 5-fold or 6-fold? Does A ever surpass C, or does C just stay dominant?
It really makes you think about, what are the underlying mechanisms that are driving this sumset growth? It's clearly not just about the initial size of the set, but, the structure and how the elements are kind of working together.
Exactly, and that's why it's still an open problem. Yeah.
Because we don't have that answer.
Okay, so problem 1, we've got fluctuation going on. What about problem 3? Does that offer any other interesting insights?
Yeah, so problem 3 kind of looks at a scenario similar to problem 2. So we're talking about two sets with the same number of elements.
Okay.
But now, instead of saying, okay, if one sumset is larger,
Right.
it's saying, okay, what if one set starts with a smaller sumset?
Okay.
Will its sumsets always be smaller?
So the inverse of that dominance question, like if it's falling behind early on, is it destined to always have smaller sumsets?
Exactly. And so, Nathanson kind of proposes that if one set starts with a smaller sumset, it might actually mean that its sumsets will always be smaller.
Okay, that makes sense intuitively. I guess, if it's struggling to generate those sums early on, it might just continue to lag behind.
Yeah, so he basically proposes that, if the h-fold sumset of A is smaller than the h-fold sumset of B for some h,
Yeah.
then it's probably true for all h after that. But we need like rigorous proof to really confirm that, right?
Absolutely.
Intuition is helpful, but...
You can't just base math on intuition.
Yeah, exactly. Okay, so these open problems are really highlighting how much we still don't know. It's like we've just scratched the surface.
Exactly.
Okay, so problem 3, kind of looking at that inverse of dominance. What about problem 4? That seems to be taking a slightly different approach.
Yeah, so problem 4 is looking at what information about the original set can we actually get just by looking at the sequence of its sumset sizes.
Okay, so it's like, can we read the story of the set through the lens of its sumset sizes?
Exactly. Yeah, and so can we figure out anything about its structure or, its unique characteristics just by those numbers?
Can we reconstruct the blueprint of the house by the shadows it casts?
Exactly. Yeah, it's really interesting.
That's a great way to put it, yeah. Okay, what about problems 5 and 6? Do they kind of continue down that path of like decoding this language of sumsets?
Yeah, so problems 5 and 6 kind of take us in a couple of new directions. So problem 5 looks at what are called restricted sumsets.
Okay.
So this is where we have rules about which elements we can add together.
So instead of just any two from the set, we might say you can only add ones that are different from each other or only ones that meet certain criteria.
Exactly.
Yeah.
Yeah. So it's adding like another layer of complexity to it.
Okay.
And then problem 6 kind of takes us beyond the number line.
Oh, okay. Where does it go?
And it looks at sumsets in the context of lattice points.
So instead of just points on a line, we're talking about points in like a grid or even higher dimensions.
Exactly. Yeah, it's really interesting.
Wow, this has been quite a journey.
Yeah, it has.
We started with simple addition, and we've ended up exploring these open problems that are kind of pushing the boundaries of additive number theory.
Exactly. And that's the great thing about math is there's always something more to learn.
Yeah, it feels like we've only just begun to uncover the hidden depths of this seemingly straightforward concept.
Yeah.
I think I speak for all our listeners out there, the math lovers, when I say, we can't wait to see what new questions are going to rise in the future and what mysteries are going to be solved.
Exactly. And for anyone who wants to explore this a bit more on their own, I highly recommend taking a look at the table in Appendix A of his paper.
Okay.
It gives some really concrete examples of sumset sizes for a specific class of sets, so you can kind of see these patterns firsthand.
That's a great way to kind of solidify the understanding and continue the adventure on your own.
So as we conclude this episode, I think the big takeaway is that even the most basic mathematical operations can have these really profound depths to them.
Right.
And, there's always more to explore, more to discover, and just keep asking those questions, keep seeking patterns and embracing those possibilities.
Couldn't have said it better myself.
Yeah.
Until next time, keep those mathematical minds curious and engaged. Welcome to the Deep Dive. We're diving deep today into additive number theory, specifically sumset sizes, right? We're going to be looking at Melvin B. Nathanson's paper, Inverse problems for sumset sizes of finite sets of integers.
Sounds a bit intimidating, I know, but it's a really fascinating area.
Yeah, I mean, even simple addition can get pretty complex, huh?
Absolutely. This paper really shows that, how simple operations lead to really complex questions, sometimes even ones we don't have answers to yet.
That's what we're here for, to unravel those complexities.
Exactly.
But maybe we can start with the basics for our listeners.
Yeah.
What exactly are sumsets and their sizes?
Okay, so let's imagine you have a finite set of integers. We'll call it A. The h-fold sumset of A, written as HA, is basically the set of all possible sums. You get it by adding h elements from that original set A.
Okay, so like if our set A is, say, 1, 2, 5, and we want the twofold sumset
Right.
2A, we'd add every possible pair of elements from A, even add an element to itself. So 2A would be 2, 3, 4, 6, 7, 10.
You got it.
And the size of a sumset, we show that with those bars, like 2A.
Right, those vertical bar.
It's just the number of elements in the sumset. So
Right.
2A would be 6 in this case.
Precisely.
Right, so we've got our set A, its eightfold sumset, HA, and the size, HA. Now, what kinds of questions are mathematicians trying to figure out with these?
Well, Nathanson's paper focuses on two big categories of questions: direct problems and inverse problems.
Let's start with the direct problems. What are those all about?
They're basically about understanding how the sizes of these sumsets behave as we increase, that number of elements we add together.
So we know our set A, and we want to know what happens to the size of HA as H grows bigger and bigger.
Yeah, exactly. And that's where those first few theorems come in, like theorem 1.
What does theorem 1 tell us?
It says that as you keep making these A-fold sumsets, they eventually settle into a predictable kind of form.
Interesting.
They start looking like a continuous interval of integers,
Ah, okay.
sometimes with a few extra elements at the edges, but yeah, it stabilizes.
So there's like an order to how they grow, not just random numbers all over the place.
Yeah, there's a structure that emerges.
That's pretty cool.
And theorem 2 gets even more specific about how those sumset sizes grow.
Okay, what does it say?
Theorem 2 says that eventually those sizes form an arithmetic progression. The difference between consecutive sumset sizes becomes a constant.
Like a pattern.
Exactly.
Can we see an example?
Sure. Take the set A, 0, 2, 3. If you calculate the sumsets, you get 2A is 0, 2, 4, 5, 6, 3A is 0, 2, 4, 6, 7, 8, 9, and so on.
Okay.
The sizes are AA equals 3, 2A equals 5, 3A equals 7.
Oh, I see. Increasing by 2 each time.
Right, an arithmetic progression.
That's so neat.
Right, just simple addition, but leading to these predictable patterns.
Yeah.
And then we have Leb's theorem, which is theorem 3.
Okay, another theorem about sumset sizes. What does that one tell us?
This one gives us a lower bound for the size of the sumset. It basically says the size of HA can't be smaller than the size of the previous one, H1A, plus a certain value. This value depends on the original set size and how much the sumset sizes are increasing.
So it's like a limit on how small a sumset can be.
Exactly. It puts boundaries on the growth.
But how is that different from theorem 2? I mean, that one also deals with the growth of sumset sizes, right?
It's all about when each theorem is most useful. Theorem 2, the one with the arithmetic progression, that works best when the sumsets have stabilized into that interval-like pattern.
Right, right.
Usually for larger values of h. But for those early stages where h is smaller, Leb's theorem, that's the one with the lower bound, that helps us analyze those initial steps.
Okay, so each theorem has its own sort of sweet spot where it's most useful.
Exactly. And they all work together to give us this this framework to understand how sumset sizes change.
This is fascinating. But you mentioned inverse problems before.
Right.
How do those differ from these direct problems we've been talking about?
Well, now, instead of knowing the set and figuring out the sumset sizes, we do the opposite.
Oh, interesting.
We get the sumset sizes A, 2A, 3A, and so on, and we have to try to figure out what the original set A was.
Okay, so it's like working backwards. We're given the clues, the sumset sizes, and we need to solve for the unknown, the original set. Sounds tricky.
It is.
But is it always possible to find that original set just from knowing its sumset sizes?
That's a great question, and it brings us to some really intriguing parts of Nathanson's work.
Uh-oh, sounds like there might be some surprises in store.
It turns out it might not be as straightforward as we'd hope. Before we dive into that, though, we need to talk about affine equivalence.
Okay, let's unpack that. What is affine equivalence, and how does it relate to all of this?
So, two sets are considered affinely equivalent if you can transform one into the other by scaling and shifting it.
Scaling and shifting.
Yeah.
Like multiplying all the elements by a constant and then maybe adding or subtracting something?
Exactly. For example, the sets 0, 2, and 1, 4 are affinely equivalent.
Okay.
You just multiply the first set by 23, and then add 23 to each element, and you get the second set.
So even if those sets look different at first glance, they share some kind of underlying structure
Right.
because of that scaling and shifting relationship.
Exactly. And here's the crucial part. Affinely equivalent sets always have the same sequence of sumset sizes.
Wait, hold on. So if we know the sumset sizes, we might not be able to tell which of those affinely equivalent sets is the original one.
You got it. That's the problem.
That makes things a lot more complicated. So knowing the sumset sizes doesn't guarantee that we can uniquely determine the original set.
Right.
That's not good news for our inverse problem, is it?
It makes it much more interesting, that's for sure.
So where do we go from here?
Well, that's where things get really interesting.
Okay, so affine equivalence can make things a bit messy when we're trying to solve those inverse problems. But does Nathanson give us specific examples of this ambiguity in action?
Absolutely. That's where theorem 4 comes in. It basically confirms what we were just talking about. Even if two sets have the same number of elements and they give us the same sequence of sumset sizes, they might not be the same set.
Wait, so even with those constraints, we could still end up with multiple possibilities for the original set. How is that even possible?
It's pretty counterintuitive, right? But Nathanson lays it out in the proof. He gives us two specific sets to illustrate it. A, 0, 2, 7, and B is 0, 3, 7. Both sets have 3 elements.
Okay, so they have the same number of elements. Let's walk through the calculations then and see how this plays out. I need to see it to believe it.
Great idea. Let's start with the twofold sumsets. 2a is 0, 2, 4, 7, 9, 14, and 2b is 0, 3, 6, 7, 10, 14. Both of those have 6 elements.
Okay, so the sizes match so far. What about their threefold sumsets?
For 3a, we get 0, 2, 4, 6, 7, 9, 11, 14, 16, 21. And for 3b, it's 0, 3, 6, 7, 9, 10, 13, 14, 17, 21. Both of them have 10 elements.
Starting to see the pattern here. But just to be thorough, let's calculate the fourfold sumsets too.
All right, so for 4a, we have 0, 2, 4, 6, 7, 8, 9, 11, 13, 14, 16, 18, 21, 23, 28. And for 4b, we get 0, 3, 6, 7, 9, 10, 12, 13, 14, 16, 17, 20, 21, 24, 28. Again, both have 15 elements.
Wow, okay, so A and B are clearly different sets, but their twofold, threefold, and fourfold sumsets all have the same sizes. That's pretty wild.
And if we think back to those earlier theorems, theorems 1 and 2, this pattern actually continues for all their larger sumsets.
Really?
Yeah, both A and B will eventually stabilize into those sumsets that look like intervals with a few extra elements maybe, and their sizes will always match up.
So what does this actually tell us about the inverse problem? Does this mean it's impossible to solve?
It means it's a lot trickier than we might have thought initially. We can't always be sure we've found the exact original set just from the sumset sizes, but it doesn't mean we can't learn anything.
Okay, good. So there's still hope. What other tools or, I don't know, insights does Nathanson offer to help us deal with this complexity, especially with these inverse problems?
Well, Theorem 5 is especially helpful here. It deals with a specific kind of set, sets that are formed by taking an interval of consecutive integers and adding one extra element that's outside that interval. And the theorem actually gives us a formula for figuring out the sumset sizes for sets that look like this.
So it's like a specialized tool for a very particular kind of set.
Yeah, exactly. And they're important because they show some really interesting patterns. It's like a stepping stone. We can use what we learn from these special cases to understand the bigger picture, the more general inverse problem.
Okay, that makes sense. I'm intrigued. Let's take a closer look at this Theorem 5 and its formula. Sometimes seeing the specifics helps these abstract ideas make more sense.
Absolutely. So Theorem 5 focuses on sets that look like this 0a.
Okay.
We're taking all the integers from 0 up to some integer arrow, and then we add one extra element, w, which has to be bigger than n.
Got it. So A determines the size of that initial interval, and what is that lone wolf out there on its own?
Exactly. So let's say we have a set A sub 0, 4a, 7.
Okay, I see. So year is 4 and W is 7.
Right. Now let's say we want to figure out the size of its threefold sumset, 3a sub sub.
So H is 3 in this case. What do we do first?
The formula in Theorem 5 actually has two parts, and we use one or the other depending on the relationship between W and he.
Okay.
In our example, W is 7 and he is 3 times 4, which is 12. So W is less than he, and we'll use the first part of the formula.
Makes sense. Now that first part of the formula includes a term, J sub 0 sub. What's that all about?
It's basically a helper variable that tells us about the overlap between certain intervals in the sumset. We calculate it as J sub 0 sub, H plus 1 W, where those square brackets mean we take the greatest integer that's less than or equal to the value inside.
Ah, okay. Let's plug in our numbers then. J sub 0 sub would be 3 plus 1, 7, 4, which is ms3, 4. So j sub 0 sub is nis is 1.
Exactly. And now we're ready to use that first part of Theorem 5's formula.
Okay, hit me with it.
It's hey sub j sub 0 sub plus 1 plus h j sub 0 sub 2 plus aris j sub 0 sub plus 1, 2. Substituting our values, we get 3a sub nizar is 1, 7 plus 1 plus 3 nizar is 1, 2 plus 4, 3 nizar 1 plus 1, 2.
Time for some careful calculation. What do we get?
Simplifying step by step, it's 3a sub, I give you a7 plus 1 plus 4, 2 plus 4, 5, 2, which is 3a sub plus 4, 22, 2. Then 3a sub equals near 6 plus 44. And finally, 3a sub equals 38.
Okay, so the threefold sumset for our set 0, 47 has a size of 38. We got there just using the formula.
And the cool thing is, this formula works for any set of this form, no matter what you and there are.
I'm starting to see why Nathanson focuses on these sets. They have this structure we can actually quantify and use to our advantage.
Exactly, and it leads to some really interesting patterns, which Nathanson actually shows in his experimental data in Appendix A.
Experimental data always sounds exciting. What kind of data is he looking at here?
He gives us a table showing some set sizes for a bunch of sets of the form 0, 4 area. He keeps constant at 4 and calculates some set sizes for different values of W, all the way from 5 to 50.
So he's essentially playing around with that W element, seeing how it changes things. What kind of patterns did he find?
Well, one really interesting thing is that you can have two different sets with different DUA values, but their sumset sizes will be identical for a while. Then all of a sudden, the sizes start to diverge.
That's strange. Can you give us an example from the data?
Sure. Look at the sets a sub 9 sub 0, 4 and a sub 10 sub equals 0, 4, 10. Their sumset sizes are the same all the way up to the two-fold sumsets, both with a size of 15. But then from the three-fold sumsets onwards, they start to differ. A sub 10 subs sumsets grow faster than a sub 9 subs.
It's like they're neck and neck in a race. Then a sub 10 sub suddenly pulls ahead.
And this isn't just a coincidence. Nathanson proves that this can happen mathematically in Theorem 6.
So Theorem 6 gives a formal explanation for this observation from his experimental data.
Exactly. It states that for any set size and any number of initial sumsets we choose, we can always find two sets that will have matching sumset sizes up to a point and then diverge afterward.
Now, I really want to know how he proves that. Can we look at the proof of Theorem 6?
Of course. The proof actually shows us how to create these sets with the behavior we want. Let's say we want two sets, each with 5 elements, and we want their sumset sizes to match up to the threefold sumsets, but diverge after that.
Okay.
So that means K, the size of the set, is 5, and H sub 1 sub, the point where they start to differ, is 3.
Following the proof, the first step would be to calculate A, which is K2, so E would be 3 in our case. Then we calculate W, which is H sub 1 sub plus 1.
Yeah.
That gives us W3 plus 1, 3 equal 12.
Perfect. Now, the proof tells us to consider these two sets, A, H, A double, which is 0, 3, 12 in our case, and B, 0, W plus 1, which is 0, 3, 5, 5.
So we've constructed our two sets based on the values of K and H sub 1 sub. Now we need to show that their sumset sizes do indeed match up to H sub 1 sub and then diverge.
Right. Let's calculate their sumset sizes up to their threefold sumsets. We can use Theorem 5 for that.
Okay.
For H1, 2, and 3, both of these sets will fall under the second part of Theorem 5's formula because W will be greater than H.
So we can use that formula. A sub H plus 1 plus 2. Let's plug in H, 1, 2, and 3 and see what we get.
All right, so for H1, we get 1A, 1 plus 1, 3, 1 plus 2, 2, 2, and 1B equals 1 plus 1, 3, 1 plus 2, 2 equals 5 as well. The one-fold sumset sizes match. Now for H2, it's 2A equals 1, 3, 2 plus 2, 2 plus 10, and 2B equals 3, 2 plus 2, 2 plus 2 equals 10. Still matching.
Great. What about HC3?
For H3, we have 3A equals 3 plus 1, 3, 3 plus 2, and 3B equals 3 plus 1, 3, 3 plus 2, 2 equals 22. As expected, their threefold sumset sizes match.
Perfect. So we confirmed that the sets we constructed have identical sumset sizes up to H sub 1 sub. Now the next step is to show that when H is greater than H sub 1 sub, the sizes diverge.
Exactly. Let's calculate their fourfold sumset sizes, where H sub 1 sub plus 1 plus 1 sub. Now things get a little trickier here. For set A, W12 is less than A, which is 4, 3 equals 12. So we'll use the first part of Theorem 5's formula. But for set B, W plus 1 equals 13 is greater than A, so we'll stick with the second part of the formula.
Okay, so our calculations are going to split here. Let's start with set A. We need to figure out J sub 0 sub, which is 4 plus 1, 12, 3. That simplifies to negative 7, 3, so J sub 0 sub is negative 3.
Now, plugging that into the first part of Theorem 5's formula, we get 4a equals negative 312 plus 1 plus 4, negative 32 plus 3, 4, negative 3 plus 1. 2, simplifying, we have 4a equals negative 36 plus 1 plus 7, 2 plus 3, 8, 2, which is 4a equals negative 35 plus 96. 2, further simplifying to 4a equals negative 35 plus 91, and finally 4a equals 56.
Okay, got it. Now for set B, using the second part of the formula, we get 4b, 4 plus 1, 3, 4 plus 2, which is 4b equals 5, 14, 2, giving us 4b, 35.
And there you have it. 4a is 56 and 4b is 35. Their fourfold sumset sizes are different, and if we kept going calculating for even larger h, we'd see that B's sumsets always grow faster than A's.
Wow, that's incredible. We've literally built these two sets that perfectly demonstrate what Theorem 6 is talking about.
Yeah.
It's mind-blowing that just knowing the sumset sizes doesn't tell the whole story. Multiple sets can hide behind those same sizes.
That's exactly what makes Nathanson's work so fascinating. It raises more questions than it answers, which is, in my opinion, the sign of truly groundbreaking research.
It definitely leaves us wanting to explore further. Now, I'm really curious about those open problems he talks about in his paper. They sound like the perfect jumping off point for anyone who wants to keep digging into this world of sumset sizes. So we've seen some pretty amazing patterns in these sumset sizes, but I'm curious, where does Nathanson leave us? Like, what are the big unanswered questions?
That's the best part. His paper is packed with open problems, really pushing the limits of what we know. He lays out 6 specific problems that he's basically challenging other mathematicians to tackle.
Ooh, a call to action. I love it. Let's hear him. What's the first problem he throws out there?
Problem 1 digs even deeper into that idea of sumset sizes diverging, like we saw in Theorem 6.
Right, where they match for a bit and then some sets take off.
Exactly. But he asks if things can get even more complicated. Can we find sets where the sumset sizes, leapfrog each other?
Leapfrog? I'm intrigued. What do you mean?
So some sets are larger for a while, then the other sets get bigger, then the first sets are larger again, and so on. Back and forth.
Like a real battle for first place.
Exactly. And Nathanson gives us an example to think about. 3 sets, A equals 0, 4, B equals 0, 1, 3, 6, and C equals 0, 1, 3, 7. If you calculate their sumset sizes, you'll see this leapfrogging behavior.
So he's basically found this really interesting phenomenon, but doesn't fully understand it yet. He's inviting others to join the investigation.
Yeah, exactly. And the other problems he poses build on these ideas, really making us think about how much we can actually know about a set just from its sumset sizes.
Okay, so what's problem 2 all about?
It's like this. If a set is ahead in terms of its sumset sizes, will it always stay ahead?
Okay, so if one set sumset is larger than another set sumset at some point, will it always be larger from that point on?
Precisely. Can it ever be overtaken again? It gets us thinking about whether there are some fundamental properties of sets that would determine that.
So it's like asking, if one runner overtakes another, are they guaranteed to win the race? Or can they be overtaken again?
A great analogy. And then problem 3 sort of flips that idea. It focuses on the set that's behind.
Okay, so if a sumset is smaller at some point, is it doomed to always stay smaller? Like if a runner falls behind, can they ever catch up? Or are they stuck in last place forever?
It really makes you question those assumptions about how sumsets change and grow.
So it's all about challenging our intuitions.
Yeah.
And what about problem 4? That one sounds like a really big one.
It is. It's the core of the inverse problem, really. It asks, what can we truly learn about a set if all we know is its sumset sizes? Is there some deeper structure we can uncover, or are we always going to be limited by that ambiguity we saw with Theorem 4?
It's like trying to figure out what an object looks like just by looking at its shadow, right? You get some clues, but the full picture might stay hidden.
That's a great way to put it. Nathanson's work really highlights that struggle between what we can figure out and what remains a mystery.
It's exciting. It leaves so much room for discovery.
Right. And he doesn't stop there. Problems 5 and 6 take things even further.
Lead the way. Tell me more.
Problem 5 suggests we look at what are called restricted sumsets. That's where there are rules about which elements we're allowed to add together. It adds a whole other layer of complexity.
So like adding constraints to the game, making things even more challenging.
Exactly. And then problem 6, it jumps out of the world of integers completely. It wants us to think about these same concepts, but in higher dimensions, in something called the additive group of lattice points.
Whoa, lattice points. That sounds pretty advanced.
It is, but it just shows that there are so many other mathematical areas where these ideas could be explored. Nathanson is basically opening the door to a whole new world of possibilities.
Well, this has been an absolute mind-blowing deep dive. We started with simple addition and ended up grappling with some seriously deep mathematical questions.
It just goes to show sometimes the most basic operations can lead to the most profound discoveries.
I know I'm walking away with a whole new appreciation for the power of curiosity and the elegance of mathematics.
Me too. Nathanson has given us amazing tools and a roadmap for the future, but the exploration is far from over.
Exactly. So to all our listeners out there, if you're feeling inspired, dive into those open problems, see what you can discover. Who knows, maybe you'll be the one to crack the code of sumset sizes.
Thanks for joining us on this journey.
Welcome to the deep dive. Today, we're diving deep into sumsets. You know, those sets you get when you add elements from another set,
Yeah, sounds pretty straightforward, right?
like basic addition, but
It gets complicated really fast.
yeah.
Yeah.
So for all of you math enthusiasts out there, get ready, because the math behind sumsets is, well, it's incredibly complex.
It really is. It's fascinating how quickly you can go from simple addition to these like really intricate patterns and even unsolved problems in math.
Okay, so before we get ahead of ourselves, can we
Yeah.
back up just a bit?
Sure.
Define a sumset for us.
Yeah. So a sumset, it involves adding elements from a set, like you said.
Right.
And the notation AA, that represents the AFE-fold sumset of a set A.
Okay.
What that means is it's the set of all possible sums that you get when you add 8 elements from set A.
Got it.
So like, for example, let's say A is the set 1, 2.
Okay.
Then 2A would be 2, 3, 4, because you have 1 plus 1, 1 plus 2, 1 plus 2 plus 3, and 2 plus 2 equals 4.
So we're basically taking all the combinations, adding a specific number of elements.
Yeah, exactly. From that original set. Okay, that makes sense. Now, the research mentions this idea of normalized sets.
Right.
What are those, and why do we even care about them when we're looking at sumsets?
Yeah. So normalized sets, they're kind of like a way to simplify things without losing any of the general, the general idea.
Right.
So a normalized set is a set where the smallest element is 0,
Mm-hmm.
and the greatest common divisor of all the elements in the set is 1.
Okay.
It's kind of like when you simplify a fraction. Like you're making the numbers smaller and easier to work with, but you're not actually changing the value of the fraction itself.
It's like finding a common ground.
Exactly.
Okay, so once we have our set, and it's normalized, what are the main problems or challenges that we face when we start dealing with sumsets?
So there are two main problems that mathematicians are really interested in: the direct problem and the inverse problem.
Okay.
And the direct problem is all about figuring out like how big HA is, the size of HA.
So like how many elements are in it? Exactly how many elements are in the sumset as you keep adding more and more elements.
Okay.
So we want to know, how does the size of that sumset change as you add more elements from the original set?
Right, and it seems like you would just keep growing. But I have a feeling it's not that simple.
You're absolutely right.
Yeah.
It's not always just going to grow forever.
Okay.
And watch the key results from the research, theorem 2. It tells us that if H is large enough,
Okay.
the size of HA, it actually forms an arithmetic progression.
So it starts increasing at a constant rate after a certain point.
Exactly. Yeah.
Interesting. What's so important about that? Like, why do we even care that it becomes predictable like that?
Well, think about it this way. Sumsets, they come from this like really simple operation addition, but then they start showing this like really predictable behavior after a while.
Right?
And that's really important in a lot of fields like cryptography or coding theory,
Okay.
where, understanding these kind of predictable aspects of things that might seem random. Yeah.
Is really, really key.
Okay, so that's really fascinating that even though we start with something simple like adding,
Yeah.
it actually becomes very structured and predictable. And the research also talks about theorem 1,
Right.
which I think is related to that idea.
It is.
So what is theorem 1 telling us about how HA is structured when H is large?
Yeah. So theorem 1, it kind of goes a step deeper, and it looks at like what's actually inside these predictable sumsets.
Okay.
And it says that for a large enough H, the H-fold sumset, HA, can be expressed as like the union of two sets, C plus HD. So you're taking a set C and adding H copies of a set D.
Okay.
And then there's this extra set of, what they call exceptions. But the important thing is that this set of exceptions, it's always smaller than D.
So we're not just like knowing the size, we're actually starting to see what's inside it.
Exactly.
Okay, I'm with you. So, but what are C and D in this whole picture?
Right. So C, that's a very specific subset of our original set A.
And then D, that's what we call the difference set of A.
The difference set.
Yeah, and to understand D, imagine you take every possible difference between pairs of elements in A.
Okay.
So you subtract every element from every other element. And that collection of differences, that's your difference set.
Oh, so we're kind of breaking this big HA down into smaller, more manageable pieces.
Exactly.
Why is that so important? What do we gain by doing that?
So by breaking it down like this, we can analyze like how HA grows much more precisely.
Right.
We can look at the properties of C and D and understand like why HA eventually starts forming that arithmetic progression and this deeper understanding that's like super important for developing efficient algorithms, for solving problems in computational number theory, all kinds of cool stuff.
All right. So we've gone from simple addition to basically dissecting the very structure of these large sumsets.
Yeah.
But I'm guessing things get a little more complicated when HA is small.
You guessed it. That's where the real challenge lies.
So you're saying that we have a good handle on what happens when H is large.
Yeah, pretty much.
But when H is small, predicting the size of HA becomes a lot more difficult.
It really does. It's kind of like, knowing the destination of a trip, but you don't have a map for the first few miles.
Yeah, no GPS signal.
Exactly.
Okay, so what tools do we have to deal with these smaller sumsets? Like, how do we even begin to understand them?
Well, Theorem 3 gives us a bit of a hand.
Do they?
It provides what we call a lower bound for the size of HA, and this is especially helpful when H is small.
So what is a lower bound? Like, what does that even mean?
Yeah, so a lower bound is basically a guarantee. It tells us that the sumset can't be smaller than a certain value.
Okay.
So we may not know the exact size, but at least we know it can't be any smaller than this lower bound.
All right, so it's kind of like a safety net.
Exactly.
We know it can't go below this point. Okay. Now, we've talked a lot about the direct problem.
Right.
But what about the inverse problem? What makes that one so interesting?
Yeah. So the inverse problem, it's kind of like the flip side of the direct problem.
Okay.
Instead of starting with a set and figuring out the size of its sumsets, we start with the sizes of the sumsets and we ask, can we work backwards and figure out what the original set A was?
Ooh. So it's like trying to solve a puzzle in reverse.
Exactly. And it's not always easy or even possible sometimes. It's like trying to figure out the ingredients of a cake just by tasting it.
Yeah, that sounds trippy. So is it even possible to like uniquely determine that original set just from knowing the sizes of its sumsets?
So that's where things get really, really interesting. In Theorem 4, it gives us a really surprising answer.
Okay, I'm intrigued. Tell me more. What does Theorem 4 say about this relationship between sumset sizes and the original set?
So with Theorem 4, it basically challenges a very common assumption that we tend to make.
Okay.
It shows that just because two sets have the same sumset sizes, it doesn't mean those two sets have to be the same.
Wait, hold on. So you're saying that two sets can have totally different elements, but when you calculate their sumsets, they end up having the same number of elements.
Exactly.
How is that even possible?
It seems counterintuitive, right?
Yeah, but the research, it gives us some really concrete examples.
Okay.
So for example, let's take the set 027 and the set 037. Now they both have three elements,
Okay.
but if you go ahead and calculate their twofold, threefold, and fourfold sumsets, you'll find that they have the exact same sizes.
Wow, that's wild. So it's like having two completely different recipes that somehow produce cakes of the same size,
Even though the ingredients are totally different.
Exactly. It's mind-blowing, right?
Yeah, it really challenges the idea that sumset sizes are like a unique fingerprint for a set.
It does. And this has huge implications for areas like data analysis, pattern recognition, all sorts of things. It tells us that we can't just rely on these like aggregate measures like sumset sizes to uniquely identify structures. We might need more information. We might need more sophisticated techniques.
It's a bit like realizing that two suspects might have the same shoe size, but that doesn't mean they're the same person.
Exactly. It's just one piece of the puzzle.
Right. You need more evidence. Okay, wow, this is already blowing my mind, and we've just scratched the surface here. What other kinds of fascinating sets does the research dive into?
So one really interesting type of set that they look at in the research is what they call an interval plus one set.
Interval plus one, what is that?
Yeah, so it's basically an interval, like a consecutive set of integers, and then you just add one extra element that's outside of that interval.
Oh, okay, so like give me an example.
So yeah, so let's say you have the set 0, 1, 2, 3, 4, 10.
Yeah.
So you have the interval from 0 to 4, and then you have this 10 just kind of hanging out there by itself.
Yeah, like an outlier or something.
Exactly. And Theorem 5 in the research, it gives us these specific formulas for calculating the sizes of the sumsets for these interval plus one sets.
Okay, I'm curious. What's so special about these interval plus one sets? Like, why do we care about them so much?
Well, they're kind of like a bridge between these really structured sets, like intervals, and then the more kind of crazy arbitrary sets.
Okay, so they're like a stepping stone to understanding those more complex ones.
Exactly. And they let us see how that extra element, the one that's outside the interval, how that affects the growth of the sum set.
Right, right, because
Okay.
everything else is so predictable within the interval itself.
Exactly. And Theorem 5, it tells us that the formulas for calculating the sum set sizes, they actually depend on this variable called J0.
Okay, remind me, what is J0 again?
Yeah, so J0, it's basically determined by the value of that extra element,
Okay.
the one that's outside the interval.
Okay.
And it kind of tells you how far that extra element is from like the boundaries of the interval.
Okay, so it's like a measure of how out of place that element is.
Yeah, exactly. And depending on the value of J0, different formulas kick in.
Wow, that's fascinating. So that one little element, depending on its value, it actually changes the whole formula for how the sum set grows.
It does, yeah. And, it's really cool because it shows how even a single element can have this huge impact.
It's all about the placement.
Exactly. Now, Theorem 6, that looks at a totally different scenario. It asks this really interesting question.
Okay, lay it on me. What's the question?
The question is, can you have two sets, right? Where their sum set sizes are like the same for a while, but then one set's sum sets just start getting bigger and bigger than the other ones.
It's like they're neck and neck for a while, and then one of them just takes off.
Yeah, exactly.
Interesting. So what's the significance of this question? Like, why do we care if one set's sum sets eventually outgrow the other?
Well, you might think that if two sets have similar sum sets at the beginning, they'll just kind of keep behaving similarly, right?
I think so, yeah.
But Theorem 6, it actually proves that's not always true. It gives us a way to construct these two sets that have the same sum set sizes up to a certain point.
Okay.
But then after that point, boom, one set just starts taking over.
Okay, so can you explain a little bit about how they actually construct these sets? Like, how do they make sure that the sum set sizes are the same for a while and then diverge like that?
Yeah, so they use this really clever combination of intervals and those extra elements that we talked about.
Okay.
So you have these two sets, each with an interval part, right?
Okay.
And those intervals are designed so that their sum sets match up to a certain point.
Okay.
But then the extra elements in each set, they're positioned in a way that after that point,
Okay.
one set starts generating way more unique sums than the other set.
It's like they have a secret weapon that kicks in at a specific time.
Exactly. And it shows that even sets that seem really similar at first, they can have these subtle differences that only show up when you look at those higher order sum sets.
Right. So it's all about those hidden differences.
Exactly.
Now, even with all these fascinating theorems, the research also talks about these unanswered questions.
Yeah,
Open problems.
absolutely. And those are like the really exciting frontiers in this whole area.
It's where the real mystery lies.
Yeah, exactly. It means there's still so much that we don't know about sum sets, even with all these amazing results that we've already found.
So let's talk about some of these open problems.
Yeah.
What are some of the big mysteries that mathematicians are still grappling with?
Well, there's 6 open problems outlined in the paper, and they really push the boundaries of what we know about additive number theory.
Okay, so let's start with problem 1. What's the main question it poses?
So problem 1, it asks this really interesting question.
Okay.
Remember how Theorem 6 showed us that one set's sum sets can be smaller at first, then equal, and then always bigger?
Right, like that overtaking scenario.
Yeah, exactly. But problem 1 asks, could those sum set sizes actually fluctuate back and forth?
Oh, so instead of one set clearly winning, it could be more of a back and forth battle.
Yeah, exactly. So imagine you have two sets, A and B, and they're the same size.
Okay.
Could it be that, for example, 2A is bigger than 2B, but then 3A is smaller than 3B, and then 4A is bigger again?
So like a constant tug of war.
Yeah, like a real nail biter.
That would be wild. What would that even mean if those sizes could fluctuate like that?
Well, it would mean that the way sum set sizes grow, it's even more complex than we thought.
Okay, so it would basically challenge all our current models and understanding.
It would. And it would also make it a lot harder to predict how sum sets behave, if they can just swing back and forth like that.
Yeah, it'd be like trying to predict the stock market when the trends keep reversing all the time.
Exactly. And the research actually gives us a little hint that this kind of fluctuation might be possible. They provide this example with 3 sets, A, B, and C, where we do see some of that back and forth behavior.
Really? Oh, tell me more about that example.
Yeah, so the sets have sizes. A is 5, B is 4, and C is also 4.
Okay.
Now, if you look at their sumset sizes, for the two-fold sumsets, 2a is 9, 2b is 9, and 2c is 11.
Okay, so A and B are tied there.
Right, they start off the same. But then for the threefold sumsets, 3a is 13, 3b jumps to 15, and 3c goes up to 17.
Okay, so B takes the lead there.
It does, yeah. But then for the fourfold sumsets, 4a is 17, 4b is 21, 4c is 24.
So A catches back up and even surpasses B. Wow, so there's definitely some fluctuation going on there.
There is, but the thing is, the sizes of the sets themselves aren't all equal in this example.
Right.
Remember, problem 1 specifically asks about sets of equal size.
Okay, so this example, it's suggestive, but it doesn't quite give us a definitive answer.
Yeah, exactly. It's just a tantalizing clue that this fluctuation might be possible.
But we need more evidence to say for sure.
We do. It's an open problem waiting for someone to solve it.
I love it. Now, problem 2, it seemed to take a slightly different approach to this idea of one set's sumsets overtaking another.
It does, yeah.
So what's the focus there?
So problem 2, it focuses on sets of equal size.
Okay.
And it asks, if one set's sumset is bigger at the beginning, does it always stay bigger for those higher order sumsets?
So it's asking if that initial advantage is like a permanent lead.
Exactly. So let's say 2a is bigger than 2b for sets that are the same size. Does that automatically mean like 5a is also going to be bigger than 5b and so on?
Right, right. So it's questioning whether that initial lead guarantees a long-term victory.
Exactly. And it's tempting to think that it would, right?
Yeah, you would think so.
But, you know, in math, we can't just rely on intuition.
Right.
We got to prove things rigorously.
Absolutely. So problem 2 is basically saying, hey, don't assume that the winner at the start is always the winner in the end.
Yeah, exactly. We need to dig deeper and see if those sumset size advantages are like fleeting or if they can really hold up in the long run.
I like that. Now, what about problem 3? How did that relate to this whole idea of having a head start?
So problem 3, it's kind of like the flip side of problem 2.
Okay.
It says that if one set's sumset is smaller at the beginning for sets of equal size, then it always stays smaller.
Wow. So it's basically saying that if you fall behind, you're never going to catch up.
Yeah, that's the implication.
That's intense. So even if we find just one instance where HA is smaller than HB, we can automatically say that all the subsequent sumsets of A are also going to be smaller than those of B.
That's what problem 3 suggests, yeah. It's a pretty bold statement.
It's a tough break for those sets that start off small.
It is. And problem 3, it actually has another interesting implication.
Okay.
It implies that, you know, if H0A is less than H0B for some specific value of H0, then HA is less than or equal to HB for all values of H that are smaller than or equal to H0.
So if a set's some sets fall behind at a certain point, they can't just magically jump ahead for smaller values of H.
Exactly.
It's like a one-way street for some set growth.
Yeah.
Once you start lagging behind, you can't suddenly overtake.
Exactly.
Wow, these open problems are really shaking up my assumptions about how some set sizes behave. It's like a whole new world of possibilities and uncertainties.
Yeah, and it shows that even something as seemingly simple as adding elements from a set can have these deep, complex consequences.
Okay, so we've covered problems 1, 2, and 3. What about problem 4? What new angle does that one introduce?
So problem 4, it takes a step back and looks at the big picture.
Okay.
It asks this fundamental question. What can we actually learn about the structure of the original set just by knowing the sizes of its sumsets?
Oh, interesting. So if we have this sequence of sumset sizes, like all the values of HA for all values of H,
Right.
can we actually work backwards and figure out something about the structure of set A itself?
That's the question.
And is that even possible?
Well, that's what problem 4 wants us to investigate. It's like asking how much information is really encoded in those sumset sizes.
It's like trying to reconstruct a statue just by looking at its shadow. You can get some hints about its shape, but you might miss a lot of details.
That's a great analogy. Problem 4 is basically saying, hey, don't assume that you can fully understand the original set just by looking at its sumset sizes.
Right. There might be hidden structures, relationships within the set that you just can't see from the sumsets alone.
Exactly. It's a reminder that we need to be careful and not jump to conclusions.
Okay, so problem 4 is a call for caution, a reminder that there might be more to this story than meets the eye. These open problems are really making me appreciate the depth and complexity hidden within this seemingly simple concept of adding elements from a set. Now continue in the next response with part 3 of 3. So we've got 2 more open problems to cover, problems 5 and 6. What new territory do these take us into?
Yeah, so these last two problems, they really broaden the scope of, what we're looking at.
Okay.
Problem 5, it wants us to consider similar inverse problems, but this time for what are called restricted sumsets.
Okay, restricted sumsets. Remind me what those are again. How are they different from the regular sumsets?
Right, yeah. So remember how in regular sumsets, we could just add any elements from the set, like you could add the same element to itself multiple times.
Mm-hmm.
Well, in restricted sumsets, you can only add each element once.
Oh, okay. So each element has to make a unique contribution to the sum.
Exactly, exactly. And these restricted sumsets, we denote them with this little hat on the edge. So like, oh.
Okay, always. So for example, if our set A was 1, 2, what would the restricted sumset 2A look like?
So for 2a, we can only use each element once. So we can only have 1 plus 2, which is 3.
Right, because we can't do 1 plus 1 or 2 plus 2 in this case.
Exactly. So the restricted sumset 2a would just be 3.
Okay, so it's like we're adding a new rule to our game, which obviously changes the outcome.
Yeah, yeah. It's like adding a constraint to our recipe.
So how does this whole restriction thing affect the inverse problem?
Well, it makes things even more complicated, right?
Right.
Because now we're asking, can we still figure out the original set A if we only know the sizes of its restricted sumsets?
It's like trying to solve a puzzle, but with some of the pieces missing.
Exactly. Exactly. And that makes it a lot harder to, get a complete picture.
Makes sense. Okay, so problem 5 is all about figuring out if we can still crack the code even with this added restriction.
Yeah.
What about problem 6? Does that one take us in a totally different direction?
Problem 6 is really interesting. It takes us beyond those integers that we've been talking about, on the number line.
Okay.
And it says, what if we look at these inverse problems in higher dimensional space?
Whoa, higher dimensional space. Okay, paint me a picture here. What are we talking about?
So imagine instead of just a line of integers, you have like a grid of points.
Okay.
And each point on this grid, it has coordinates that are all integers. And this grid, it can be in 2 dimensions, 3 dimensions, even higher dimensions.
Okay, so like a 3D chessboard, but with potentially even more dimensions.
Yeah, exactly. And these points on the grid, they're called lattice points.
Lattice points.
In problem 6, it wants us to see if we can apply these ideas of sumsets and inverse problems to these sets of lattice points.
So we're basically taking everything we've learned about sumsets on a flat surface and trying to apply it to this multi-dimensional world.
Exactly. It's like, we've been playing checkers, and now problem 6 is saying, hey, let's try playing 3D chess.
Whoa. It's a whole new level of complexity.
Yeah.
But why is this so significant? Like, why do we care about sumsets in higher dimensions?
Well, for one thing, it's just a natural progression. We want to see how far we can push these ideas, how far we can generalize them.
Right, right. It's all about exploring the boundaries of mathematics.
Exactly. And, higher dimensional spaces, they pop up all over math and physics.
Right.
So understanding how sumsets behave in these spaces, it could have all sorts of cool applications that we haven't even thought of yet.
It's like opening up a whole new dimension of mathematical possibility.
It is. And it really pushes us to develop new tools and techniques, new ways of thinking.
Wow. This has been an incredible deep dive. We've covered so much ground, from basic definitions to these mind-blowing theorems and unsolved mysteries. It's amazing to think that something as seemingly simple as addition can lead to such rich and complex mathematics.
It really shows you the power of math,
Yeah.
How even the simplest ideas can have these deep, far-reaching consequences.
Absolutely. And before we wrap things up, what are some key takeaways that you think our listeners should walk away with?
I think the biggest takeaway is that sumsets, they're way more than just simple addition. They have these intricate patterns, these surprising properties, and there's still so much that we don't know about them. It's a really active area of research with lots of open questions waiting to be answered.
Folks have only just begun to scratch the surface.
Exactly. And, the cool thing is you don't have to be a professional mathematician to explore these ideas.
Right. Anyone can play around with sumsets, try to discover patterns, see what they can come up with.
Exactly. And who knows, maybe one of our listeners will be the one to solve one of those open problems.
That would be amazing. So to all our listeners out there, we encourage you to keep exploring, keep that curiosity alive, and keep diving deep.
Absolutely. Because there's a whole world of fascinating math out there just waiting to be discovered.
And that's all the time we have for today's deep dive. Thank you so much for joining us on this mathematical adventure.
Yeah, it's been a pleasure. And until next time, keep those minds curious.
Welcome to another deep dive. Today, we're going to be taking a plunge into the fascinating world of sumset sizes,
Oh, yeah?
in additive number theory, and we're going to be guided by Melvin B. Nathanson's paper, Inverse Problems for Sumset Sizes of Finite Sets of Integers.
Okay.
Now, while adding numbers might seem super elementary, trust me, when we start talking about sumsets, things get surprisingly intricate.
Yeah, it's fascinating how, like, a simple operation, like adding, when applied repeatedly to sets, can reveal these really intricate patterns and lead to some pretty challenging mathematical questions.
Absolutely. So before we get lost in all the, intricacies, let's make sure we're on the same page here.
Right.
Can you give us a quick refresher on what a sumset even is?
Of course. Imagine you have a set of numbers. Let's say the set 1, 2, 3.
Okay.
The twofold sumset of this set, we'll call it 2A,
Okay.
would be all the possible sums you get by adding any two numbers from the set, including adding a number to itself.
Right.
So in this case, 2A would be the set 2, 3, 4, 5, 6.
Okay, so we're essentially exploring all the possible combinations we can create through addition within a given set.
Exactly.
And the paper that we're diving into tackles both the direct and inverse problems related to these sumsets. Can you kind of elaborate on what those problems entail?
Yeah, so the direct problem is, I guess, what you might expect given a set. We want to understand how the sizes of its sumsets behave as we keep adding the set to itself.
Okay.
We're looking for patterns, formulas, anything that helps us predict those sizes.
Okay, so it's like mapping out the landscape of sumset growth.
Exactly.
What about the inverse problem? What makes that so intriguing?
So the inverse problem is we flip the script. We say, if we only know the sizes of the sumsets, can we work backwards to figure out what the original set was?
Interesting.
Can we deduce the ingredients just by looking at the size of the cake, so to speak?
That sounds like a real mathematical detective story.
It is.
And Nathanson's paper delves into some key theorems that provide insights into both of these problems.
Yeah.
Shall we start by unpacking some of the theorems related to the direct problem?
Yeah, absolutely. One of the kind of foundational results in the paper is what he calls Theorem 1.
Okay.
It essentially provides kind of a structural description of how sumsets behave when we repeatedly add a set to itself.
Okay, so it gives us sort of a blueprint for how these sumsets evolve.
Yeah, blueprint's a good word for it.
Can you walk us through the details of this theorem?
Certainly. So Theorem 1 says that if we have what's called a normalized set, and we'll get into the notation and all that stuff a little bit later.
Okay.
But essentially a normalized set is just a set where the smallest element is 0 and the greatest common divisor of all the elements is 1.
Okay.
So if we have a normalized set A, then for a sufficiently large H, the H hold sumset HA can be expressed as the union of 3 distinct parts.
Interesting. So we're breaking down the sumset into 3 segments. What do those segments look like?
Yeah, so the first segment is denoted as C in the paper.
Okay.
And it consists of sums formed primarily using elements from the quote-unquote front of the set, A.
Okay.
So think of it as the initial combinations you get before you start incorporating elements from further down the line in A.
So C captures those early sums that are heavily influenced by the smaller elements of A.
Exactly.
What about the second segment?
So the second segment is a long interval. It's denoted as bracket C, comma H times a minus D bracket.
Okay.
This interval arises from more balanced combinations of elements from A, where we're now using elements from across the entire set.
Right.
This is where the true additive character of the set starts to shine through.
Okay, so it's like we've moved past the initial bias towards smaller elements and are now incorporating the full range of A into our sums. And what about the final segment?
So the final segment is denoted as parenthesis HA minus D parenthesis, and it sort of mirrors the first segment, C. It consists of sums formed by taking the largest element of HA, which is simply H times the largest element of A, and subtracting elements of a set D, which is analogous to C, but focusing on the quote-unquote tail of the set A.
So it's like a symmetrical reflection of the first segment, capturing those sums that are heavily influenced by the larger elements of A.
Precisely.
And this 3-part structure emerges regardless of the specific elements in the original set A.
Exactly. That's the beauty of it.
Wow.
It reveals a fundamental pattern in how sumsets evolve, a kind of structural blueprint that emerges as we keep adding the set to itself.
That's incredible. Now, I'm curious about how this structural insight translates into understanding the sizes of these sumsets.
Right.
Does Theorem 1 lead to any conclusions about how those sizes behave?
It certainly does. So Theorem 2 takes the structural information from Theorem 1.
Okay.
And it tells us that once we reach that stable 3-part structure, The sizes of the sum sets denoted as the cardinality of HA
Okay.
form what's called an arithmetic progression.
An arithmetic progression. So that means that they increase in a very regular, predictable way.
Exactly. It means that the difference between consecutive sum set sizes becomes constant,
Okay.
creating a linear pattern of growth.
So it's like we're building a staircase
Yeah,
where each step has the same height.
exactly.
And this predictable growth emerges directly from that three-part structure described in Theorem 1.
The proof of Theorem 2 hinges on the fact that the middle interval, that long stretch of balanced sums,
Yeah.
dominates the size of the sum set.
Yeah.
As this interval grows linearly with h, so does the size of the overall h-fold sum set.
That makes perfect sense.
Yeah.
It's like that middle section is setting the pace for the entire sum set's growth.
Right.
Now, I also noticed that Theorem 3 takes a slightly different approach to understanding sum set sizes. Can you tell us a bit about that?
Yeah, so Theorem 3, which is attributed to Lev,
Okay.
focuses on providing a lower bound for the size of the h-fold sum set.
Oh,
It essentially tells us that even for smaller values of h, before that stable three-part structure has fully emerged, the sum set can't shrink below a certain size.
so it's like a safety net, ensuring that the sum set doesn't get too small,
That's a great way to put it.
even in those early stages where the structure might still be evolving.
Right. And the proof of this theorem relies on a clever counting argument
Okay.
that tracks how new elements are introduced into the sum set as we increase h.
So it's about carefully analyzing the growth process and proving that the sum set can't grow too slowly.
Exactly. It establishes a floor for the growth rate,
Okay.
a minimum number of new elements that must be added at each step.
Okay, that makes sense. So we have Theorem 1 giving us the structural blueprint, Theorem 2 telling us about the predictable linear growth,
Right.
and Theorem 3 providing a lower bound to ensure the sum set doesn't shrink too much. Together, these theorems paint a pretty comprehensive picture of how sum set sizes behave when we repeatedly add a set to itself.
They do. They provide a really powerful set of tools
Yeah,
for analyzing and predicting sum set growth in the direct problem.
this is already fascinating. And we've only just begun to explore the direct problem.
Right.
I'm eager to delve into the inverse problem and see what mysteries unfold there. But before we do, I think we should take a closer look at some of the mathematical notations used in the paper to make sure we're all on the same page.
You're absolutely right. Clarifying the notation will make our journey through the more intricate parts of the paper much smoother.
Yeah.
Where would you like to start?
Well, I noticed the paper frequently uses the concept of a normalized set.
Right.
Could you explain what that means and why it's important in this context?
Of course. So a normalized set is essentially a simplified representation of any finite set of integers with at least two elements.
Okay.
To normalize a set, we shift it so that its smallest element becomes 0, and then we divide all the elements by their greatest common divisor.
So it's like we're stripping away any unnecessary baggage and getting to the core structure of this set.
Yeah.
Why is this normalization important when studying sum sets?
Well, normalization allows us to focus on the essential additive properties of the set without getting bogged down by arbitrary shifts or scaling factors.
Okay.
It's like looking at a blueprint where all the measurements are relative to a common origin.
Right.
This simplification makes the analysis much more manageable and reveals patterns that might otherwise be obscured.
That makes perfect sense. And I see the paper often uses the notation HA to represent the H-fold sum set.
Right.
Can you remind us what that means exactly?
Yeah, the notation HA simply means taking the original set A and adding it to itself H times.
Okay.
So 2A would represent the two-fold sum set, 3A, the three-fold sum set, and so on.
Right. So each time we increase H,
Yeah,
we're essentially adding another layer of the original set to the sum set.
exactly.
It's like building a tower where
Yeah.
each level is a copy of the original set.
Right.
Now, what about the absolute value symbols used around HA? Like this vertical bar, what do they signify?
So in this context, the absolute value symbols don't refer to the magnitude of a number as they typically do.
Yeah.
Instead, they denote the cardinality of the set, which simply means the number of elements in the set.
Ah, so vertical bar tells us how many distinct elements are in the eightfold sum set.
Exactly.
It's a way to quantify the size of the sum set, which is one of the key aspects we're investigating.
Precisely understanding how vertical bar changes as we increase h
Right.
is at the heart of both the direct and inverse problems.
Okay, that clears up some of the notation out. I think we're ready to tackle the inverse problem and see what insights Nathanson's paper offers in that domain. But before we do that, do you think it would be helpful to walk through the proof of Theorem 1 in detail? I know it can get a bit technical, but I think understanding the logic behind the proof could really solidify our grasp of this foundational result.
I completely agree. Diving into the proof will not only solidify our understanding, but also showcase the elegance and rigor of mathematical reasoning.
Yeah.
Shall we embark on that journey now?
Let's do it.
Yeah.
I'm ready to unpack the proof and see how those three distinct parts of the sum set emerge.
All right, so let's delve into the proof of Theorem 1.
Okay.
Remember, our goal is to show that for a normalized set, A, the H-fold sumset HA eventually decomposes into these three distinct parts.
Right.
An initial segment C, a middle interval bracket C comma ha minus D bracket, and then a final segment parenthesis ha minus D parenthesis that mirrors C.
Right. And this structure should emerge when H is sufficiently large, meaning we've added the set to itself enough times.
Precisely. And the proof utilizes the properties of normalized sets and leverages some clever arguments involving modular arithmetic and divisibility.
Okay.
It's a beautiful example of how seemingly simple concepts can be combined to prove a really powerful result.
Eager to see how it all unfolds. Where do we begin?
So the proof starts by establishing the existence of these three segments.
Okay.
We won't go into every single detail.
Okay.
But the key idea is to show that as H increases, the sums in HA begin to cluster in these distinct regions.
So initially the sums might be scattered somewhat randomly, but as we keep adding A to itself,
Right.
a pattern emerges with sums concentrating in these specific zones.
Exactly. The initial segment C consists of sums formed using mostly smaller elements from A.
Okay.
Imagine starting with the smallest element of A, which is 0, since A is normalized,
Right.
and adding other elements to it. These sums will be relatively small and will tend to cluster near the beginning of HA.
That makes sense. It's like those early combinations are anchored by the smaller elements of A.
Right.
And how does the middle interval bracket C comma ha minus D bracket come into play?
So as H increases, we start incorporating elements from across the entire set A into our sums.
Okay.
These more balanced combinations
Yeah.
result in sums that fall within a certain range, which eventually forms the middle interval.
Okay, so it's like the middle interval represents a sweet spot where we've moved beyond the dominance of the smaller elements
Exactly.
and are now seeing the full spectrum of A reflected in our sums.
Precisely. And this interval grows linearly with H, meaning as we add more copies of A, this middle section expands proportionally.
That's starting to make sense. Now, what about that final segment, parentheses, hey, minus D parentheses? How does it emerge as a mirror image of the initial segment?
So the final segment arises from kind of a clever symmetry argument.
Okay.
We know that the largest element in HA is simply H times the largest element in A.
Okay.
Let's call this largest element M.
Okay, so the upper bound of our sum set is determined by that largest element A.
Exactly. Now consider the sums formed by taking M and subtracting elements from A.
Okay.
These sums will cluster near the end of HA.
That's like we're flipping the script starting from the top and working our way down.
Precisely. And the key insight is that these quote-unquote subtraction sums, M minus elements of A,
Right.
exhibit a structure similar to the addition sums we saw in the initial segment C.
So there's a kind of symmetry between building sums from the bottom up, using the smaller elements, and building sums from the top down using the larger element.
Exactly. And that's how the final segment parenthesis C ha minus D parenthesis emerges as kind of a reflection of the initial segment C.
That's a beautiful insight.
Yeah.
I'm starting to see how these three segments emerge and why they form this stable structure for large enough H.
Right. And the proof goes on to formally demonstrate that these segments indeed cover all the elements in HA, leaving no gaps. This involves some careful arguments involving modular arithmetic and the properties of normalized sets, which we won't delve into here.
I trust that those arguments are sound. So we've established the existence of these three segments, but how do we know when this structure emerges when H is large enough? The theorem mentions a value A0 of A.
Right.
What is that?
Excellent question. The value A0 of A represents a threshold that depends on the specific set A.
Okay.
It's a bound that guarantees that for any H greater than or equal to A0 of A,
Okay.
the H-fold sumset will exhibit this three-part structure.
Okay, so it's like a tipping point
Yeah.
where the sum set settles into this predictable pattern.
Exactly.
And I recall you mentioning earlier that the original bound for A0 of A has been improved over time. Can you elaborate on that?
Yeah, so the original proof by Nathanson provided a bound that depended on the square of the largest element in the set A.
Okay.
However, subsequent work by mathematicians like Granville, Schicken, and Walker has significantly tightened this bound.
So they've shown that the structure emerges even sooner than originally thought.
Exactly. Their refined bound depends only linearly on the largest element of A.
Wow.
demonstrating that the stable structure arises much earlier in the process of repeated addition.
That's impressive.
Yeah,
It's a testament to the iterative nature of mathematical research,
it is.
where new insights constantly refine and deepen our understanding of even seemingly well-established concepts.
Absolutely. And this improved bound not only strengthens the theorem, but also has implications for other areas of additive number theory,
Right.
where the structure of sumsets plays a crucial role.
I'm starting to appreciate the depth and interconnectedness of this field.
Yeah.
Now, I think we have a solid understanding of Theorem 1 and its proof. Should we move on to explore the other theorems related to the direct problem?
Absolutely. Theorem 2, as we touched upon earlier, builds directly upon the foundation laid by Theorem 1.
Okay.
It states that once we've reached that stable three-part structure, the sizes of the sumsets, that is, the values of vertical bar, h, vertical bar, form an arithmetic progression.
Right. It's that staircase pattern we were visualizing earlier.
Mm-hmm.
Can you walk us through the proof of Theorem 2
Sure.
and show how it connects to the structural insights from Theorem 1?
Certainly. The proof essentially quantifies the dominance of the middle interval in that three-part structure. Remember, the middle interval bracket C comma high minus D bracket grows linearly with H.
Right. It's like that middle section is expanding at a steady pace, setting the tempo for the entire sumset.
Precisely. The proof carefully analyzes how each of the three segments contributes to the overall size of the sumset. It shows that the contributions of the initial and final segments become relatively insignificant as H grows larger.
So it's like the middle interval is the driving force behind the sumset's growth,
Right.
while the other segments become mere passengers.
That's a great analogy. And as the middle interval grows linearly, the overall size of the H-fold sumset also increases linearly,
Okay.
leading to that arithmetic progression in the values of vertical bar, HA vertical bar.
Okay, I see how the linear growth of that middle section dictates the overall behavior of the sumset size.
Right.
Now, Theorem 3 takes a slightly different approach, focusing on a lower bound for sumset sizes.
Yeah.
Can you remind us what that means and why it's significant?
Of course. So Theorem 3, which is attributed to Lev,
Right.
tells us that even for smaller values of H before that stable structure has fully emerged,
Yeah.
the H-fold sumset can't shrink below a certain size. It provides kind of a minimum guarantee, a floor for how small a vertical bar can be.
Right. It's like a safety net, ensuring that the sumset doesn't become too small,
That's a great way to put it.
even in those early stages where the structure might still be in flux.
Exactly.
Yeah.
And the proof of this theorem utilizes a clever counting argument.
Okay.
It focuses on how new elements are introduced into the sumset as we increase H, showing that there's a minimum number of new elements that must be added at each step.
So it's about analyzing the growth process,
Mm-hmm.
improving that the sumset can't grow too slowly, that there's a minimum pace it must maintain.
Precisely. The proof carefully tracks the addition of new elements, establishing a lower bound for the growth rate of the sumset size.
Okay, that makes sense. So we have these three theorems working together to provide a comprehensive understanding of sumset sizes in the direct problem.
Right.
Theorem 1 gives us the structural blueprint. Theorem 2 describes the predictable linear growth, and Theorem 3 establishes a lower bound. It's amazing how much insight we can gain from seemingly simple concepts like repeated addition.
It's a testament to the power of mathematical reasoning, how we can start with basic operations and uncover these deep patterns and structures
Yeah.
that govern the behavior of numbers. And we've only just begun to explore the fascinating world of sumsets.
I'm eager to delve into the inverse problem and see what challenges and insights await us there. Shall we embark on that journey now?
Absolutely. The inverse problem takes us into the realm of mathematical detective work,
Right.
where we'll try to unravel the mysteries hidden within the sizes of sumsets.
Okay, so let's dive into this inverse problem.
Yeah.
Now, this is where things get particularly intriguing.
Yeah.
We're essentially asking if we know the sizes of the sumsets, that is the values of like vertical bar, HA, vertical bar for various H's,
Right.
can we reconstruct the original set, A?
Right. And as you might imagine or expect, the inverse problem is significantly more challenging
Yeah.
than the direct problem. It's a bit like trying to solve a jigsaw puzzle, where you only have the outline and the number of pieces, but not the individual pieces themselves.
So there's a level of ambiguity inherent in the inverse problem,
Exactly.
where multiple sets might potentially lead to the same sumset sizes.
Precisely. And Theorem 4 in Nathanson's paper confirms this intuition. It states that knowing the sumset sizes doesn't always guarantee a unique solution.
So we might encounter situations where multiple sets, despite having different elements,
Right.
produce sumsets with identical sizes,
Exactly. It's like having different musical scales that, despite having distinct notes, produce melodies with the same number of notes.
Okay, I'm starting to see the challenges inherent in the inverse problem.
Yeah.
Can you give us an example of two different sets that lead to the same sumset sizes?
Certainly. Consider the sets A equals 0, 2, 7
Okay.
and B equals 0, 3, 7.
Okay.
These sets are distinct, but if you calculate their sumsets 2A, 3A, 4A, and so on, and similarly for B, you'll find that the cardinality of HA equals the cardinality of HB for all H.
Wow, so those two sets, despite having different elements,
Right.
produce sumsets with the same number of elements at each step.
Yeah,
That really highlights the ambiguity we're dealing with.
it does.
So if simply knowing the sumset sizes doesn't always lead us back to a unique original set, are there any tools or strategies we can use to navigate this ambiguity?
Yes, there are. While the inverse problem is inherently challenging, mathematicians have developed techniques to extract as much information as possible from sumset sizes.
Okay.
Theorem 5 in Nathanson's paper, for example, provides a set of formulas for calculating sumset sizes for a specific family of sets.
Intriguing.
Huh.
What kind of sets does Theorem 5 deal with?
So Theorem 5 focuses on sets that are constructed by taking a consecutive range of numbers and then adding one extra element outside that range.
So it's like having a perfectly ordered line of numbers
Yeah.
and then someone jumps in line, disrupting the pattern.
That's a great way to visualize it.
Okay.
And the formulas in Theorem 5 provide a systematic way to calculate the sumset sizes for these types of sets, taking into account the position of that line jumper.
Okay, so it's a specialized tool for analyzing a particular family of sets.
Right.
Can you give us a sense of what these formulas look like and how they work?
Certainly, the formulas in Theorem 5 are a bit intricate, but I can break down the key ideas. Essentially, they involve dividing the calculation into two cases. Case 1, the extra element is relatively close to the consecutive range. In this case, the impact of the extra element on the sumset size is more nuanced. The formula involves calculating a value called J0, which essentially measures the degree of overlap between certain intervals within the sumset.
So J0 quantifies how much disruption the extra element causes to the otherwise neat structure of the sumset.
Exactly. And the formula uses J0 to carefully account for these overlaps, ensuring that we're not double counting elements in our calculation of the sumset size.
Okay.
Case 2, the extra element is far away from the consecutive range. If the extra element is sufficiently far from the consecutive range, its impact is more straightforward. The sumset size is simply determined by the size of the consecutive range and the value of H. It's as if the extra element is so far out that it doesn't significantly disrupt the overall pattern of the sumset.
So the formulas essentially provide a roadmap for calculating sumset sizes in these specific scenarios.
Yes.
Taking into account the position of that extra element
Right.
and its degree of influence on the sumset structure.
Precisely. They offer a powerful tool for analyzing and predicting sumset sizes for this specific family of sets,
Right.
providing valuable insights into how different arrangements of elements can influence the final sumset size.
This is really helpful. I'm starting to see how mathematicians are developing these specialized tools and techniques to tackle the complexities of the inverse problem.
Right.
Now, I know Nathanson's paper goes on to explore other facets of sumset behavior,
It does.
including a fascinating result about the relative growth of sumsets for different sets.
Yeah.
Can you tell us a bit about Theorem 6?
Absolutely. Theorem 6 delves into the dynamics of sumset growth for different sets. It addresses a question that might seem quite intuitive. Can we have two sets where their sumsets initially have the same sizes, but then at some point one set's sumsets start growing larger?
So it's like two runners in a race who are neck and neck for a while, but then one suddenly pulls ahead.
That's a fantastic analogy. And Theorem 6 proves that this overtaking phenomenon is indeed possible in the world of sumsets.
Intriguing. So we can have two sets that start off seemingly in sync
Yeah.
with their sumsets having the same number of elements.
Right.
But then something shifts and one set sumsets start to outgrow the others.
Exactly. The paper even provides specific sets as examples to demonstrate this behavior. And the proof involves carefully constructing these sets, A and B, in a way that ensures their sumsets initially match in size, but then diverge due to subtle differences in their structure.
So it's like setting up a race where the runners are evenly matched for the first few laps, but then one runner has a hidden advantage
Right.
that allows them to eventually surge ahead.
That's a great way to visualize it. The proof highlights how even subtle differences in the arrangement of elements within sets
Yeah.
can have a profound impact on the long-term behavior of their sumsets.
This is getting really fascinating. It's like we're peeling back layers of complexity
Yeah.
and revealing these intricate relationships between seemingly simple operations like addition and the underlying structure of sets.
And as we delve deeper into this field, we encounter more and more unanswered questions, mysteries that continue to intrigue and challenge mathematicians.
Speaking of mysteries, I know Nathanson's paper concludes by presenting several open problems,
It does.
questions that are still waiting to be fully solved. I'm always eager to hear about the frontiers of knowledge.
Of course.
So I'd love to explore some of these open problems with you. What are some of the most puzzling questions that mathematicians are grappling with in the realm of sumsets?
So one of the open problems that Nathanson poses is whether the sum set sizes of two distinct sets can leapfrog each other multiple times. In other words, can we have two sets A and B such that the cardinality of HA is greater than the cardinality of HB for some values of H, but then the cardinality of HB becomes greater than the cardinality of HA for other values of H. And this pattern of flip-flopping continues as H increases.
So it's like those two runners in our race keep overtaking each other.
Exactly. It's a question about the oscillatory behavior of sum set sizes and whether this kind of back and forth dynamic can persist indefinitely.
That's a really fascinating question, and it highlights how even in a field as seemingly well-defined as additive number theory,
Right.
there are still these deep mysteries lurking beneath the surface.
Absolutely. Another open problem relates to the concept of eventual dominance. If one set's sumset is larger at some point, will its sumsets always be larger from that point onward, or can the other set's sumsets catch up and even surpass it again? It's a question about the long-term behavior of sumset growth and whether a temporary advantage necessarily translates into lasting dominance.
So it's like asking whether a runner who takes the lead at some point in the race
Right.
is guaranteed to win, or whether another runner might still have a chance to make a comeback.
Precisely. It's a question about the dynamics of sumset growth and the conditions under which one set sumsets might eventually and permanently outgrow another's.
And Nathanson poses some other really intriguing open problems as well, doesn't he?
He does. He asks, for example, if having a smaller sumset at some point implies that all preceding sumsets were also smaller. It's a question about the monotonicity of sumset growth and whether a late bloomer can ever have an early lead. He also wonders what other hidden information about the original set might be encoded within the patterns of its sumset sizes. Are there certain properties of the original set that can be inferred or even uniquely determined just by looking at how its sumset sizes evolve?
So it's like we're trying to read the story of the original set
Yes,
just by looking at the footprints left by its sumsets.
exactly. It's a beautiful metaphor for the kind of detective work that mathematicians are engaged in as they try to uncover the hidden relationships between sets and their sumsets.
And finally, Nathanson suggests extending these investigations beyond the realm of standard integer addition. He proposes exploring similar questions with different types of addition, such as addition modulo, a prime number.
Right.
This opens up a whole new landscape of possibilities and challenges, pushing the boundaries of our understanding of sumsets and their behavior.
Absolutely.
Right.
It's a reminder that even within a seemingly specific and well-defined area of mathematics, there's always room for exploration and discovery. By tweaking the rules of the game, by changing the way we add or the types of sets we consider, we can uncover entirely new patterns and structures that deepen our understanding of the mathematical universe.
This has been a truly fascinating deep dive into the world of sumset sizes. We've explored intricate theorems, grappled with the challenges of the inverse problem, and even peered into the realm of open questions that continue to push the frontiers of mathematical research.
It's been a pleasure.
I'm left with a sense of awe at the beauty and complexity of this seemingly simple concept of adding sets together. It's a reminder that even in the most fundamental of mathematical operations, there are hidden depths waiting to be explored.
And who knows, perhaps these abstract explorations of sumset sizes might one day reveal unexpected connections to real-world phenomena. The patterns we uncover in the behavior of numbers could hold the key to understanding complex systems in fields like physics, biology, or even economics. The pursuit of mathematical knowledge is a journey into the unknown, and it's a journey that's constantly revealing new wonders and connections.
Well said. That's a perfect note to end on. So until next time, keep exploring, keep questioning, and keep diving deep into the fascinating world of mathematics.